Morning, I'm Dan Freed. Pleasure of welcoming you to the CMSA and to the start of this program. Just a word about the CMSA. This is the 10th year of the CMSA. We're a center here at Harvard dedicated to the two-way interaction of mathematics and science, as you see from this program. So we run programs and workshops. Today's the start of both of those. Conferences, there's a big data conference Friday and Saturday, for example. We have lots of postdocs here. We have weekly seminars and lots of different activities that you can learn about on our website. So I'm very excited by the start of this program about mathematics and machine learning. And to kick off, we have Mike Douglas this morning speaking about math, computers, and AI.
Thanks, Dan. Thanks, everybody, for coming to the beginning of our workshop and our program. I think this will be very exciting, and I'm glad so many of you could join us. So we'll have 6 lectures this week and 2 panel discussions, the first of which at 3 o'clock today. And there'll be the big data meeting Friday and Saturday, and then the program will start Monday at 10:30. There'll be more information on the website and on the Zoom channel. So let me start. There we go. Okay. So we're going to really try to break new ground in computation as applied to mathematics. But of course, there's a very long history which goes back before the electronic computer. Computation is an essential source of mathematics. It's not, I would not call it in itself mathematics, but computation, including human computation, is one of the essential sources. We look for patterns in the data that it produces. We analyze using it. And of course, electronic computers greatly enlarged the scope of this. And in many fields of mathematics that are very large now really could not get off the ground without the ability to do long digital computations. I mean, I think this whole study of dynamical systems is a good example of that. It's just too hard to get a lot of analytic results, and one can see things on the computer. But there are many examples where in principle, it was a clear direction forward involving computation, but one just needed to wait until the computers were big enough to do it. So we're going to talk about continuing that tradition with new methods, machine learning, artificial intelligence, but of course, it's really, in many ways, not to be separated from the rest of scientific computation and computer science. And so I'll survey many areas that are relevant to the questions that we hope to discuss, and try to, obviously 90 minutes is not enough to go into depth, but to at least hit a lot of main points and give you references and ideas of what you should be studying. So, well, I mean, inspiration for this program are many interesting illuminating recent discoveries, knot theory, representation theory, number theory, PDE, and it shows the potential for doing real mathematics, but it's equally the case that there are many areas of mathematics that either where both haven't really been touched by this, and in fact, it's not totally obvious. What would I actually do with a computer if I'm studying this? And so obviously a prime question for a program like this is, well, what is it that makes a question good? What are the questions that we can hope to really contribute to substantially using these methods? So that'll be a main goal for the program. And I'd like to suggest a couple of other goals. So one is that there are big classes of problems, of course, and a significant topic or meta topic in computer sciences group together many problems that people might be studying piecemeal, or a few at a time, and assemble them into some large class of problems that can be studied systematically. And of course, there are many examples, but the one which I'll talk a bit about, which is, I think, very prototypical for us and many problems we talk about are instances of, is a constraint satisfaction and combinatorial optimization. And so these have been systematized. There are languages to express them. There are benchmarks. And so we could develop more such classes of problems, which might be interesting to computer science, but definitely interesting to mathematics, mathematical problems that can be attacked using very similar techniques and then produce benchmarks that could go on, and computer scientists and others could say, well, here's my super duper latest system. Now maybe I can solve this outstanding problem with it. And so we'll get a lot of future work happening in our problems in that way. Another direction which I think is open really is that there are, as you may have seen on the Zulip or online, there are many mathematical databases, and they tend to be used for addressing questions within the particular topic of the database of knots and so forth. But of course, there could be interesting relations between different fields and widely different fields. Of course, we know many such examples in mathematics of such relations, which are not obvious, requires deep intuition to see, but maybe some can be discovered just by looking for cross correlations between databases. So that's another direction we can look into. Okay, so that's discovery. And then another really important way in which computers have changed the way that we all think and we live is that they really are intelligence amplifiers. It was in the early days, both the AI paradigm and the IA paradigm. If you look into it, it's really true. And the IA paradigm still lives. And you could argue that the search engines have made us all substantially smarter. It's hard to quantify, but clearly many questions that you would have taken quite a while to find the answer to, the answers available. Of course, it comes with the pitfalls and dangers too, but there are many ways in which computers make us smarter, enable us to think on a more abstract or a higher level. And we would like to get into, well, what does that actually mean in terms of teaching and doing math? And again, open to discuss how one would think about and work on that. But one direction that already has a shape is to look back at earlier successes in these directions. And so to ask, well, okay, if AI has gotten so much better, maybe something that looked hard before is not so hard anymore. So for example, this landmark of computer-assisted mathematics, the computer-assisted proof of the four-color problem, verified proof now. So, well, one should, perhaps it's time to step back, So, what did we learn, or what did the graph theorists learn from this proof? I think they did, but what? Could this proof, it was a big effort, all steps of this proof were a big effort back in the day. Could it be something that now could be a PhD to reduplicate this proof for even an undergraduate project? And, perhaps you could tell, Code GPT or whatever, just produce the programs that were needed to make that proof. Another test I've always felt is that the proof was often criticized over the years as not it's this huge case analysis, what understanding that we get, but maybe some problems that the answer is just like that. It's intricate, and a better test would be to say, here's another problem kind of like that. How quickly can you now adapt your proof to resolve this new problem? That's an equally valid test. The liquid tensor experiment, many of you will have heard of this use of a lean to verify a fundamental lemma of Clausen and Schultz have their work. So again, this is there's a lot of work that on AI for theorem proving, which we'll get into, especially later in the program. We'll have a week devoted to that. Okay, so as I said, I'm going to really try to systematically go through a variety of areas of AI and computer science, which I think are very important to know something about. So let me start. Okay, so mathematical logic, clearly the foundations both of mathematics and a certain branch of computer science and artificial intelligence. And on some level, this is well understood. You've been studying for more than a century. We have a solid, definition, a good deal of understanding of what is a rigorous proof within mathematical logic. It's often called a formal proof in which all the deductive steps are defined not in terms of their meaning, but in terms of the syntactic transformation of some ingredients of the proof or some other combination or transformation from one step of the proof to the other. And if they're systematically applied properly, you're guaranteed to have a correct proof and such, so it can be verified by a machine. And then this is part of computer science, the field of a formal method. So both the interactive theorem proving that many of you will have heard about, and a sizable field that the central problem is to prove that a computer program does what you think it does what it was designed to do, its specification. Okay, so David McAllister will go into some more detail about the varieties of logics, and so I just mentioned them here. So there's propositional logic with the Boolean operations, first order logic where you can quantify over variables that take values in sets, but you can't quantify over functions. That would be higher order logic. And to express many things in mathematics, an interesting subset can be done in first order, but mostly you need higher order. And then there's a sort of in-between case where you adjoin some very controlled example of axioms that are more general. So they're often called first order logic plus some theory like integer arithmetic. And then the computational technology SAT solvers, first order logic solvers, and this will be an SMT solver. And David will explain type theory, this distinct foundational approach to the set theory of ZFC, which is in many ways natural if you program computers at all. Almost all modern programming languages have types, integer variables, floating point variables, and so forth. And so that's the first intuition. We don't allow generic variables that can take any value. They must take a value out of some particular type, which is a quote set, but not a set because it has explicit rules of construction for its elements. So the natural numbers in set theory, you could construct in many ways. This will be a standard approach, but who's to say that this set is 2 as opposed to just that set integrated some under what? But in type theory, you would define the natural numbers saying that it's either 0 or it's a successor of another natural number. There's a function that takes one and gives the rest, and that's the definition. And those are all the possible natural numbers. So it's a much more controlled framework.
So what does SMT stand for?
Satisfiability modulo theory.
So it's satisfiability.
Modulo theory. So there's some other theory, most commonly integer arithmetic, but you could imagine many where there's some sort of partial, sort of decision procedure for deciding truth of statements. Okay, so there's a long development, and David will get some into this, but one of the crucial distinctions there is between simple and dependent type theory. And to illustrate that, think about the definition of a vector. So what's a vector? It's just, in some sense, a list of this many elements of the base ring. Okay, so it could be natural, vector of natural numbers, vector of integers, or whatever. And then it's got some dimension, the number of elements. That can you define? So intuitively, you say this type is like a function of a type and the natural number. If I give the function a type, it should come back with another type vector. But can types really be the input and output of functions? Well, that's highly non-trivial to make work, and that's what the idea of the dependent type theory is. Okay, so that's one reason why people like Lean, and is that it is based on dependent type theory. Okay, so the lightning discussion there now switches to algorithms, computational complexity theory. You will all have heard of this, but the core ideas of this are really very, very central. Computer science, the things we're talking about. So we should understand the real definition of NP and NPR problem, what it means, why it is that NP is believed is different a priori and is believed to be different from a co-NP. I'll remind you of that shortly, but these are at least this much you should really understand well. And then of course there's more detailed questions which matter a great deal in practice. We need efficient algorithms. Now, if you were to pick up only one computer science book and you're a mathematician, this is certainly the book that you should pick up and study. That's Victorson's book. I mentioned Victorson's speaking at Harvard next Friday. So. Okay, what kind of hard computations do we want to do? Well, certainly a paradigmatic one for this program is to make a big database of mathematical objects of some type, like groups or knots or something. And so, well, how do you define the problem? Well, you define group or whatever it is. And then you have to define, because it's an infinite set, we can't make a database of that. But if we have some measure of size, we could say, yes, I have all the groups up to order 1 million or something like that. Knots of up to 19 crossings, which actually does exist. There are many, we have made available lists of these databases. These are a raw material resource for what we plan to do in this program. So that's one case. I should say that usually, to the extent that I've looked at this, the hard part is not generating examples. The hard part is getting a database in which there's a single instance of each isomorphic object that's actually showing that 2 knots are they isomorphic or not is highly non-trivial. I'll talk about that a bit on the next slide. And that's the hard part. And so then there are other objects where there are so many of them, and there's not like a clear structure or a clear problem that you're going to apply it to, that you don't really talk about classifying them. That's true, you classify all graphs with up to 20 vertices, but nobody bothers to do that, because it's relatively easy in some sense, although it's, again, not trivial, because graph isomorphism is not trivial, but still you're not going to find people generating a huge database of graphs because there's just not that much structure there. And nevertheless, one should think about data sets of graphs. We're going to be doing, some of what we do is data science for mathematics. And then the concept to keep in mind, and this is, I think, is very, very important in first getting into this, and sometimes not emphasized enough, is that what really means with a data set is a probability distribution over the class of objects in question. So that's what we really mean by a data set. And so these are all implicitly probability distributions, because I can say I list all the finite number of objects in that class, and I just take the uniform distribution where if I have n objects, they each have probability 1 over n. Of course, I made a choice. I could have chosen something else, but that's a very natural choice and very typically what people do when they use these data sets. And once you bring it to that's the definition, of course, you can also put a distribution on an infinite set. You just need the sum of the probabilities to converge to 1. And that's the input for all the machine learning and many other questions. There's some distribution of the objects in question. And then I would say a defining characteristic, you can see it, this sets me off a little bit, but I'm going to say it, of a math ML paper is that when they use a data set, they actually define the distribution that they're studying. And if the definition is, well, I took all the graphs in Mathematica, from Mathematica. Well, it's true, that's a definition, but you can see how kind of the critical eye, the mathematicians say, that's your definition. You can write a paper saying, I proved something about all the graphs in the Mathematica data set. Well, okay, but isn't it better to take some definition that will last for the ages? Isn't that what we aspire to as mathematicians? Even to say all the graphs with up to 20 vertices, well, at least that's a simple, canonical, simple definition, And so I think one should really think about that as a very early step in one's problem. And then there are a lot of interesting and well studied, especially in the case of graph theory, random distributions. Quite a lot is known about them. And you prove something about that, then you've done mathematics which has more of a chance of lasting, having value. There are interesting random knot models. There's a lot that you can say there.
That's the question.
Please.
So I'm not sure I totally understand why it's important to establish the distribution of objects.
Oh, okay. Well, let me make a qualification to that. Okay, so it depends what you're doing. So now if you're saying I'm looking for a counterexample to X, then you don't care that much. If you found the counterexample, you don't care about all the others. Okay, but if you're going to say something like we fit 98%, of this, this function of my objects, my network fit 98%. That means nothing without the distribution.
I'm just thinking, in a lot of practical applications of machine learning, people often typically don't know what the distribution of the objects are.
We are doing math.
Right, but even in math, right? Like it seems to me, but you correct me if you disagree, that. I guess it's the question that I'm trying to ask is to clarify what exactly you're trying to establish. So are you trying to establish some kind of bound on your generalization error given a finite?
I'm trying to say, what are the criteria that you just looking at a math paper make it more likely to have a lasting interest? And so indeed, every paper implicitly defines some distribution, but if the definition is, well, it's a combination of the objects in Mathematica and the objects in this other random data set, then who's going to read that paper in 20 years?
Well, if the output is an interesting theorem, right, then does it matter what the distribution?
Well, why did they get that interesting theorem? I mean, I agree. There are cases like the counterexample. Yes, that database contained a counterexample. I'd use that to disprove this conjecture. I agree. Interesting. But with this data set, I proved that this class of algorithms gets greater than 90% accuracy. And so it depends on the details. I quite agree. There are problems where you would find the interesting instance and use it, and then you don't care about the rest. But if you're going to make a statistical statement, then you do care about the distribution. And that includes a theorem. That includes a theorem about this.
Yeah.
That's the thing about statistical statements.
But then even there, you don't necessarily have to know the complete distribution, right? Like for certain kinds of generalization bounds, you might need to only know that it's bounded and it's
Yeah. You're coming to a much more sophisticated point of view. There's a difference between the known unknown and the unknown unknown to take the class. Yeah, that's right. So if you know that I'm boxing the quantity of interest here, that's much more sophisticated than that.
I think that can actually relate to what he's saying, and you would disagree, but like, for example, if you take the example of graphs, right? You know that edge training graphs really do not look like other typical graph in defining nature. And so you want to know what type of properties an average graph in that group looks like. And I think that's what he means by we care about the distribution.
Yeah. In practice,
it's kind of special, right? Because it's actually a probability distribution, right? Whereas like lots of other mathematical objects, presumably it's not clear what the relative.
Well, again, you might have that's right. To the extent that you can motivate the probability distribution, that's even better. I'm just saying it should be well defined, and the definition should be something simple, not I took it out of this database. So I'm perfectly happy with knots up to 19 crossings, although from some point of view you might say that was kind of arbitrary, but that's simple and clear.
I got two uses. One is distributions identifies time of class. That's going to be interesting if people will still read about it in 20 years. That's what you said.
Right.
And what you said is something else. With the distribution, I'm having now the possibility to give a weak result. It says the weak convergence. And the question is, if I choose the distribution well, maybe this weak result is going to come close to a strong one.
Right.
And there's a bit of a different use of distributions here.
Yeah, but again, I think in both cases we are at least respecting the idea that we want to think about the distribution. Right. And I'm kind of more criticizing this simpler point of view that once you have a data set, you run with it.
The distribution as a tool to give a result that's going to be relevant to years or once it's out. And distribution as a tool to give a proof of something stronger.
Yeah, no, they're both valid, and they're both using the concept of distribution and programming.
Like just one.
Yeah.
But sorry.
Yeah.
But I think it's important to point out that it's possible to cheat because there's highly structured data sets out there that have taken enormous amounts of work to produce.
Yeah, that is also true. That's
and so one needs to be careful that one is not cheating, that one's hiding all the work where someone else.
My next slide, of course, is to some extent making that point. So this was the very short summary of what went into constructing this listed the prime knots with up to 19 crossings. And this was a very non-trivial project. So there's some elementary objects that's, I guess, relatively easy to decompose a knot into the prime knots. There is a fairly straightforward over-complete construction. You have these diagrams where you have projected into the plane and things can cross over and under each other. So a graph, a four regular graph, all the vertices, have four edges coming in, can be turned into such a crossing diagram, but this, 2 to the n number of ways, and then very, very sophisticated math involved in deciding which of these things are actually isomorphic knots or possibly isomorphic to knots with fewer, what's the minimum number of processing. So it's a very, very long story. And when you say cheat, I guess you could have meant a number of things, So indeed, I mean, if you use this database, there's a great deal going into it. There's also the more machine learning or meaning of cheating to say you're going to explicitly rely on structure which was particular to that data set and doesn't generalize. And well, here again, the only restriction is that 19. So there might be features of what you're doing that fail for 20, say, but clearly any structure in this data set that doesn't claim to go beyond 19 is structure. It's not cheating.
Yeah, I mean, I think that it would be possible to, I think that this is not an example where this might happen, but in a situation in which you have it can be very difficult to describe the uniform distribution, for example. And so if I'm given this uniform distribution, then I can deduce some great theorem, but I'm still hiding the fact that someone else worked out the uniform distribution.
Yeah, I mean, I think that was the kind of thing I was trying to say in my first version of the alternative. Indeed, it was a huge amount of effort and sophistication going into this that might make some things easy to prove. Yeah, I agree. Okay, so we move on to search. So this is this classic central topic of the good old-fashioned AI. And the main problems were the obvious way to try to solve it is search. Find the paths between 2 points in a graph. And then of course the most famous that you all have seen and may have some familiar with is this playing strategy games of perfect information. And you have this game tree, you search for my best move, which then might be responded by his best move, ... So that's a classic example of search. And it's really a very core topic. There's a great deal you can, this is a classic and up-to-date textbook on many aspects of artificial intelligence, which I recommend. Search, the kind of traditional AI approach to search is to bring in heuristics. There are many algorithms that take certain inputs about the problem, and then you might add to that heuristics. Some of these inputs, so again, it's very, very broad category of things, but things that are not guaranteed to work for every problem, but do help a lot for some problems. So a very simple one, but always worth keeping in mind. If you have several search methods, K different ones that often work, and try them all. Divide up your time and try them all. Don't use all your resources on M1. And that's usually a good rule of thumb in solving a hard problem. Okay, so other standard terminology here. The cost function, you're often searching for a solution that minimizes some cost, like the length of the path, versus the value function. Okay, so a good example of this is that in chess, you might evaluate the position, the thing you might teach your 6-year-old son or daughter, that the pawn is 1, the queen is 9, and so forth. So it's a very, very rough kind of evaluation, but it has value. It's based on something, experience. You can estimate using more sophisticated things, but some sort of estimate of how good a configuration is and what the cost or value might eventually be. Okay, so now the main thing about search is that not all the cases I mentioned, but a lot of cases of search are NP-hard. And of course, the canonical defining thing is the SAT problem. You're given a Boolean formula like X and Y or Z, and you have to find some assignment, like X is true and Y is true, and Z could be true or false at that point. You just have to find one that makes the formula true. And there is a very simple algorithm for that. You choose X, you set true and try to solve, substituting true, solve the SAT problem to the resolving statement. And that might not work. Then you try X is false and you solve it for the other statement. So it's a recursive algorithm. And once you get through all the branches of this recursion, they all fail, then the formula cannot be satisfied. And it seems so trivial, I mean, who's to say that there's anything here, okay? But the important lesson of theoretical computer science is that this is this defining problem in NP. It's easy to check the solution, but it's believed to be hard to find a solution in general. And in worst cases, that there's no general way to do much better. In the worst case, it might be like 2 to the n over 2 or something like that. But that's it. And then you're not going to beat this exponentially. So that's the central problem of search and a lot of AI and theorem proving and all the rest. So what do you do about it? And there's a kind of brute force approach. Well, we program a very efficient solver. We have lots and lots of shortcuts that you can imagine doing to this. We exploit them all, and we make the code very fast. And that's what's done in SAS solvers. Okay, another thing you can do is say, well, okay, there's no general recipe. Let's look at our problem and throw in some heuristics that are good for that problem based on our experience studying the problem. That's 2. And then there's number 3, which we now have much more ability to get the computer to somehow learn the structure of the problem and learn some heuristics. And that's, of course, a very interesting and potentially transformational thing. It's not the general solution, it's somehow finding the problems that have the structure for which there is a solution. At present, I think it would be fair to say that these are competitive, and the SAS solver is often better. That we start to see cases, where this is better. It depends on the problem very much, but they're both in competition. Okay, so let me just give a quick example of the SAS solver approach. Many of you may have seen this. Is the Boolean Pythagorean triple problem. As I say, we take the integers from 1 to n, all of them, and can you split them in 2 subsets so that neither subset contains a Pythagorean triple? And Euler, Kuhlmann, and Marek showed using a SAS solver that yes, you can do it for 7824, and no, you cannot do it for 7825. And here's the example of a coloring for a 7824, where there's red, there's blue, the 2 colors, and then white means it works either way. And so how did they find that? Well, every Pythagorean triple, you introduce one variable for each of the integers. Since there's 2 colors, we'll just map them to true and false. And then each triple turns into a clause, a logical expression, which must be true. And you can easily see that the condition I mentioned says that one of the 3 colors, one of the 3 integers, A, B, C, those variables has to be true, and one of them has to be false. So if that's not the case, then we fail. Okay, so we get this long list of statements, all of that must be true, but not an infinitely long, something hundreds of thousands or 7,000 variables. So that's within the range of very big SAS solving with parallel computers and the rest and so forth. So that is a computer-assisted proof, and they actually did generate the proof. There is a way to get a logical proof out of this. It proved unclear to structure in the problem, but it worked. Okay, and then that paradigm is, in some sense, a special case of this constraint satisfaction paradigm, which I won't go into detail, but it's basically saying, why restricted is true and false. Maybe the variable can take 3 values or some finite number of values. Why just allow Boolean functions? I could have some other binary, ternary, whatever function, and so forth. So that's the general family of these constraint satisfaction problems. And then if you're trying to maximize something like, what's the largest number of Pythagorean triples or whatever the objects are, there was a problem that Jordan Ellenberg proposed involving triangles of sort. Let's try to maximize the number that we can put in the plane with a given number of points. Then that's a combinatorial optimization problem. And from some broad point of view, theory of computer science, these are all very similar problems. They're all kind of the same family. In fact, if you have a CSP, often map it into a SAT problem, which is a good one, and get it to a SAT solver. But there's a great deal known theoretically about these problems, which doesn't mean that you can always solve them, or that you know which ones can be solved. But there is a large literature that you can study, both in theory of computer science and in physics, because this is like the deepest existing connection between theoretical physics and computer science. Is this relation with statistical physics of combinatorial optimization and spin glasses and so on for you to Mazar and Montanari's type because I didn't. Okay, and maybe I have to make sure I turn more towards the microphone. Okay, this is the SMT software I mentioned. There's one called Z3 developed at Microsoft, and there's a book by the UHF with a lot of kind of puzzle math problems, but that's a very powerful thing for the things that you can do with that. There is a rich mathematical theory of these CSPs. You can phrase it as finding hypergraph when network is on. So you can see various things, like the fact that problems with binary functions are generally easier than ternary and higher functions. Okay, and then against general and important lessons that there's no universal solution for search. There's these many methods. If something works, it doesn't mean all the things will work. Of course, they'll eventually work with enough computing time, but some things can work much better than others, and that means presumably there's some kind of structure in the problem that method exploited. And so then there's always this question: so what was that structure? Okay, one slide on the interactive theorem proving. There's a lean proof that the infinitude of primes phrased as a statement that for any n there exists a prime greater than that n. That's the standard Euclid proof, and so it's verifiable by computer. It's not that hard to read. It's not that easy to read, and so this is an area of a great deal of research that could be helped quite a bit by AI. Let me not spend a lot of my time on that, but I must point it out. Okay, so we've been talking so far about in this AI context, what you could call a rule-based AI. And now we're going to switch to deep machine learning, data-driven. There are many other terms in the older literature. AI. So rather than try to understand the task and program an algorithm that solves it, or use one of these very general, program a set of constraints and use a general constraint solver. Now we're going to switch to this statistical approach. We have a task. We assemble a data set of examples of the task. We train a statistical model to recognize or generate similar examples. And so now this will get us into the mathematical data sets. And I got one, I think, wrong but substantial piece. You can't claim that all we're going to talk about is data science for mathematics, but some significant part of what we'll talk about is data science for mathematics using this synthetic data that you get from mathematics. Okay, so probably many of you have seen, but for those who haven't, let me just in a few terms, a few basic concepts of data science. And this may also be useful because, again, there's a lot of textbooks for practitioners that spell out things and the detail required to program it, but maybe not the most convenient way to think about it as a mathematician. And all the important concepts do have very concise and general mathematical definitions. So like the supervised learning again. So the basic paradigm, we have input-output pairs x, y, and we're going to train a neural network or something else to given another x produce the appropriate y. So that's fitting a function. It's so special about fitting a function. And then the general way that this is normally done in modern machine learning is that while there's some probability distribution over these XY pairs, okay, it might be what's called the imperial distribution. If you're an explicit data set, and I just draw from it with a uniform probability, but it might be some more abstract or more general distribution. And now this is the error, the difference. Of course, it might be least squares or something else, but some measure of the distance between the fitted function. I have this family of functions depending on a parameter W. And for a given function, I can compute the expectation under my data set distribution of the error. And then I'm looking for the W that minimizes that. And that's the maximum. Well, it's not an maximum likelihood of the X, it's the error minimizing. It could be maximum likelihood if I choose the right thing. And so anyways, that's the mathematical definition of supervised learning. And it's quite simple in general, and there's a large theory that starts from that definition and produces many interesting results. Self-supervised learning, well, we don't have Y. We're trying to fit the probability distribution over X. And again, there could be a general error measure of how far the fitted distribution, the model is from the actual or the empirical distribution, but a very typical one is the cross-entropy figure. Okay, so these are very broad paradigms, but they assume there's some kind of local measure of the goodness of the fit. This one in particular, I mean, it's both obvious that you can estimate this by sampling individual items from the distribution. You can say, yeah, this one fits really well, this one fits poorly. Let's produce a signal based on each item in the data set. But there are many tasks where that's not the case, you know, such as a game, where you find out at the end, yes, you win or you lose. And then you have to propagate it back and decide, well, okay, which move was the mistake that led to me losing, or you know, what was the opponent's mistake or whatever. And so that's also a very common situation. This is the case in proving a mathematical theorem, and then this is the domain of reinforcement learning, where you need to cope with this problem of predicate assignment. So you're still learning, but you don't have that local task. Okay, so they're all defined in terms of the data sets. I mean, this one is implicit. You know, if you're playing a game, there's a data set of many, many games. You know, games that we have such a computer plays against itself. But the great thing about mathematics is we have this platonic data. We have this data that we could go and discover, you know, some alien civilization, and of course don't know nothing. There'll be very little we can talk to them about. Of course, we can talk to them about the prime numbers, you know, the Riemann hypothesis, you know, all these things. We can talk about these data sets if we want. And so that's the basic mathematical object of our study. And I'll just repeat again, you're always talking about a probability distribution over some objects. It might just be uniform over a finite set, but you're always talking about that. And then always in these fits, you have this question of in distribution versus out of distribution. You know, when you're testing it, okay, I'll get into that in a moment. Maybe I should move on to that phrase here. Again, probably everybody knows, but I'll just say it. You can't just take the error defined. So the argument here, we minimize this training error on a training set to pick W, but then we cannot take this. This will always be an optimistic estimate of how good the model actually is for the obvious reason that it solved those points. It did the best it could to fit them. And now we need to test it with an independent data set, which we can usually get just by subsampling and splitting, using most of our data set for training, some of it for testing. And then there's arguments that that's likely to work. You know, this is, again, a very subtle and interesting story, you know, but that it's not a stupid thing to minimize this to get a low testing error, as long as in practice what you're interested in is testing it on the same distribution. And if you're testing it at a distribution, well, that's a much more complicated story. Okay, so there is a statistical learning theory, which I expect Boris Hannon will speak about. Ellie Grigsby will give a whole course, which I'm sure this will be an important part of. And so we have, now we're getting into a bit more practice, things that those of you who have done machine learning, well, I'll mention it. So besides the training and testing set, there's also often the validation set. What's that? And so I'll, again, just summarizing things that could be a course in machine learning. In the standard with small models and the classical statistics, you get this phenomenon where you can have too many parameters, and that's generally because the data hasn't delivered statistics. And so you might fit data coming out of a quadratic equation with noise with a 10th order polynomial and get this very nice wavy line that goes through all the points, but it's a terrible model with the quadratic. So that's the bias variance trade-off, that the model could express all this more stuff, but now it's just used it to express noise. So what do you do about that? And one of the standard cues is what's called regularization. So besides the error measuring how well it fits, you control the norm of the parameters. You say, I'm going to favor models where the parameters are small or there's few. There's many ways to do this. But in any case, I get a parameter lambda, which then it's not obvious. How do I set it? And what is usually done in practice is say, let's make a third set. Let's do the training with a variety of values of lambda. Let's then check it on this validation set and pick the lambda that gives the best result from this validation set. So, very good. That's how we chose the lambda. But now we can't accept that as a good measure of our testing error. Now we need a third testing set. That's another very general thing in practice, which is good to know about. if you came as a statistician, you might want his names, but I certainly have talked to statisticians who thought that deep learning back when 2014 say thought this was a crock. Why is deep learning a crock? It's got all these parameters. It's just hopeless. It's just going to overfit. And well, that's a very respectable argument. That's true. That is what's in all the textbooks. But nevertheless, it works. And now, of course, this just have some theory of why it is that a model with many more parameters than you need to interpolate the data can work. But very, very non-trivial and interesting theoretical question. Okay. Yeah.
Just to ground things a little bit, since we're talking about the supervised setting, should we be thinking about the input space as theorems and the output space as true false labels, or is
you could try that. That would be a really hard one. I mean, more of the kind of example we'll talk about later will be the input spaces and knots and the various values of the non-invariance for the knots. And then we're going to look for relations between non-invariants. I'll talk about that example a little later.
And so when you talk about the domain, we're talking about the space of not problems, not the space of, let's say, all theorems.
So there. So yeah, just as you say, I've been a little assuming people. Okay, so this was from Davies et al. This famous Nature article of 2021 that Morty Williamson was a co-author on another segment of this paper. But this is I believe table of all the knots with up to 19 crossings, and along with the list of knots are these list of invariants that are either numbers or polynomials or other quantities that are uniquely and canonically associated to each knot. And so, it's hard, but it's possible to compute these things. Now you can ask, are there relations? And of course, mathematicians have asked, are there relations between these things? And in particular, there's things you get from a geometric point of view, and there's things you get from an algebraic point of view as a relation between those. And that's what they looked for. They just do data science on this set. And they tried to fit they picked each column as a Y, and they took all the other columns as the X. And so that's the concrete example of the math data science that I have in mind. And I'll say it now, but some of these terms I'll come back to. Okay, so they did find good models, okay, complicated good models. And then you can ask, well, okay, what's there? What does it depend on? This is a attribution score. This tells you, yes, this good model for the signature really depends primarily on these three invariants, which are over in this geometric side of the thing. So let's stare at this for a while. They were working with Mark Black and one of the knot theorists, and they came up with this conjecture. Maybe this is the general relation that we can try to now prove mathematically. And then the DeepMind people said, oh, okay, you think it's that. Let's now let's try to use reinforcement learning to generate some counterexamples to this, which they were actually able to do. So they had to refine and modify the conjecture. And the second try worked. The second try led to this theorem. So that was an example of this math machine learning using supervised learning, which I had in mind in the previous discussion. Does that?
Yeah.
Okay.
Just a tiny erratum. So
Please.
There was no RL involved in finding the counterexample. It was much more
Hands-on.
Mark and you have just trying knots like very out of distribution.
Okay, great. Good. So anyways, could have been more automatic, but in any case, successive math and machine learning. So this was my one slide summary of a statistical learning theory. This is my one slide summary of the feed-forward networks, which again, I'm sure everybody here has seen this definition, a series of linear maps, and then some nonlinear maps, which is just a sum component-wise, direct sum over the nonlinear map by each component. And the nonlinear map could be as simple as what's called relative. If x is positive, the value is x. If x is negative, the value is 0. And then this already with just two layers, one of these sigmas, so two linear transformations, is a universal function approximator. It's a very old result, but in some ways not the most interesting result because there are lots of function approximators that require a number of parameters that grows exponentially, basically with the dimension, right? So you value at every point and you interpolate. But it is true, it's a universal approximator. Now, what's a little more interesting and yeah, Boris will get into more details of this, is that there is this large class of functions where you can do two layers without exponential, with a dimension independent number of units, which is just controlled by the error. And there is this clear, this is just precise sense in which this is working a lot like the Fourier transform. If you thought about sigma as really the Fourier transform, you would not be totally wrong in the way you think about this. You can adapt Fourier style arguments to other functions here. Okay, so that's nice, but that's not why people are so excited about feed-forward networks. This still requires a lot of units for most things, and the really powerful things come once you have many layers, and you can start to generate and learn intermediate functions, or what you could call features, in terms of which the final function becomes very much simpler. And so this is, again, well, set of mathematically well-posed questions, very central because what can be represented. Okay, so that's the question: what can be represented by some class of feed-forward neural networks? And then there's a question of, well, then given the data set, can a computer actually learn that model that represents the function again? So what's the standard learning procedure? Well, we always start with this probability distribution. And here we're doing supervised. So we're going to grant that there's some F, and maybe in general there's noise, but we've got a probability distribution here on the domain. We might have it on the domain in range if there's noise. We start with some random initial parameter for our function that we're trying to learn. So suppose this family of functions, parameters that are linear maps in the case of the feed-forward network. So we start at W0, and then we do stochastic gradient descent on that error function, or possibly a regularized error function. And what does that mean? Well, it's almost gradient descent. We compute the gradient with respect to all the weights of this error function. Okay. So if we were just doing that, it would be gradient descent. It would definitely converge to a local minimum, which might not. It's rather unlikely to be the global minimum you would think, because this is not a convex function, almost never. Okay. Now, stochastic gradient descent is almost that. But what you do is you self-sample. You have your distribution, and you say, I'm going to do this. Say 32 or 128 samples at a time. What's called a batch. I will compute that gradient, and I will take that step, and I'll take a different 32. Or I might split up my whole data set so that I have a balanced sampling between everything. But I do it in these small batches, and so you can think of that as and reasonably approximate it as a gradient descent with a noise compared to sampling the whole distribution. And so it's a stochastic gradient descent. Okay, and then that's the process, and that works much better than if you ask people 15 years ago, they would have said, how could this ever work? But it seems to work a lot. Okay, but it doesn't always work, and so this is the sort of thing that I imagine Tori and Francois and others will talk about in much more depth in the next week when we get into practical problems and methods. Suppose it works great. Suppose it doesn't work. We didn't find any good function. But why? Why is that? What would we do differently to try to find a better function? Okay, well, there's a list of possibilities. And number one is that there actually wasn't a good function in the class you were considering. And maybe you need a network with more layers. What's also quite likely in practice, especially in math, is the function you're trying to compute, given the inputs you give, is really very complicated. But if you now supply it with a feature, some predefined function of the inputs, now you've made it much easier. And being a mathematician, this is a problem which people know something about. There is a list of good features that you can try. And so that's often going to be what you do. You put in more features. Too few parameters, well, that's again possible. So long asymptotic behavior, which is the one that if you're doing standard function interpolation for like scientific computation, that's an easy way to go wrong. And that's also an easy way to go wrong here too. If you have like relative, then you get linear asymptotic significance. And if your function doesn't have linear asymptotics, well, that could be a problem. Okay, so that's probably the number one hypothesis. Bad local extrema, generally what you do about that is you try several times, and if it sometimes it works and sometimes it doesn't. That could be because of local extrema. So then you fixed it by using the case that actually worked. sample complexity. Okay, this is probably the most interesting one, is that it could be that there's a function in the class that represents the function you're interested in, but you just need too much data to actually specify that function compared to all the simpler functions that specify some part of the data. And so that's also very, very common. And if you think about real world problems with images and language, this is more or less always the case. There's just no way that the data has enough samples to fix the function that tells you whether an image is a cat, or to predict the next word in a text and so forth. And so a huge part of the story there has to be inductive bias within this class of models. Somehow decisions preferring certain models over others. And so that's when you get into the deep theoretical extraction, that's kind of the most interesting frontier. And then finally, there is this point to keep in mind that we've assumed the distribution in all of this, and we might be interested in testing it and wanted to work out a distribution, and that should be kept in mind. Okay, so that's my quick summary of that. This is going to be my obligatory quick slide about the transformer. I don't have time to do this justice, and I'm going to use my time for things I have more to say about. But the transformer obviously is a significant, a major step in the development of deep learning and transformed language modeling, and it's very helpful in modeling mathematical data sets. This question of why it's so helpful there are definitely answers out there in literature, but I don't know that there's some accepted set of there's a consensus as to the answers to that question. So that's an interesting question to look into. Okay, so supposedly 5 now. We're trying to fit some function, like I mentioned in the example.
Sorry, did you summarize transformers?
Okay, please. I was more putting this slide as a, okay, so this transformer, so it is built out of the feed-forward layers and the attention layer, and now we're going to talk about a list of vectors, or actually a set of vectors, because in themselves, the vectors don't have any ordering, so we're going to call those U sub I. And the attention layer maps those into another set of vectors, V sub I, and it maps them as basically a linear combination of the original vectors. And so that linear combination is basically 2 parts. There's a origin x on each of the vectors, which is just a linear map that you can learn. And then there's a part that sums over the various vectors on the input. Okay, so both transformations are applied. And then this is sort of a softmax overlap, if you will, it's a similarity measure with a learnable metric here. So this you can think of as a learned inner product between UI and UJ. And I really think it doesn't have to be special, a learned product. And then we're going to translate the value of that product into essentially probabilities using normalized things using this standard kind of softmax Boltzmann. And then those will be the weights with which we add the things. So that's the attention level. There's more one could say, but that's certainly that. Okay. So again, very, very powerful, allows expressing a lot of long range structure clearly very good. Much more probably to say about why it's good. Okay, so now we come to this question. I suppose we found this good model. We have this function that depends on 40 million parameters, that models our function. So what good is that, to a mathematician? It's not like we can sell it and make money. So what good is it? And so basically, we need to understand something about that function. So that's very essential here. And so there are various tools which generally developed in this engineering literature, which can be adapted to this purpose. So one very common thing to do is, of course, leave out variety, all the inputs, all the various things you put in. Let's try leaving each one out and seeing if that spoils the performance. If it still works, we could probably just leave it out. That's called depletion from the science term. There's a more sophisticated kind of attribution, which is much like a statistical significance, to say that if you've done linear regressions, t-values and things. It's that kind of thing. But to generalize it to this nonlinear setting, we can look at the gradient of the function with respect to each input. That would be a sensitivity hypothesis, how much that input contribute to the thing. Or this is, you know, or we could look at the gradients with respect to intermediate layers. The value Z is someplace in the middle of this neural network or something. And you say, well, yes, that one was very important to getting the final result. That one not so much. And you can use that to inform this relation to get a simpler model. Another very powerful technique is a symbolic regression, where you got your model, you now use software, which I won't get into, which looks for a simple algebraic expression, maybe made out of the standard operations, maybe with some special functions thrown in, but tries to fit your model. And now you could have done that in the original data set, but now, of course, you have a whole function where you can put in any input. So the symbolic regression is going to be much more powerful in that case. And they're very powerful uses of this in the science literature, where you do have a priori reasons in physics, for example, to think, yes, there really should be some simple formula that approximates, and we only really want the simple approximation anyways. So that's a case where that's very powerful. Another more sophisticated tool I mentioned is when we think that there's some feature, we have evidence that yes, this intermediate thing is important in getting the right to fit, the right outputs. But what does it actually mean? And so we might say, well, I think it means X. And I'm going to test that hypothesis by using, the most simple version would be to say, does this particular variable inside the model fit X? And of course, that's very unlikely to work because it was one component of 500-dimensional space. Why should that work? And so then you might try to do a linear regression to predict it. You might try to train another simpler neural network to predict it and so forth. There's a very nice example of that from a couple of years ago of training a transformer, so not a language model, but a transformer ab initio to recognize valid Othello games. Okay, so sequences of moves in Othello that obey the rules, and then you can ask, well, okay, it did that as a linguistic task. Did it produce a model of the board? So that's the feature. I have a black piece at this square. And they got reasonable evidence in this paper. So that's a good example of this kind of probe and intervention. Okay, so I went through the knot theory example. Unless there's a okay, I will just again remind you of it that this was an example of use of supervised learning to motivate an interesting conjecture, which actually was provable and using the attribution techniques that I talked about to get this particular suggesting that the function really had an essential dependence on these three parameters. But then it turned out that the conjecture had to depend on this parameter. So that's the strength and the limitations of that approach. It didn't actually quite get the right conjecture, but it got close enough that they could work with it.
Sorry, before you
Yeah.
can we just go back to the discussion that we had earlier? So what I remember you were saying earlier about distribution and in distribution, out of distribution, so I'm not. So what is the distribution?
There's no absolute canonical distribution.
Or is there's a set of knots that you consider?
It's an infinite set. That's why there's an issue. If it was a finite set, I'd be okay with saying, let's just study the uniform distribution.
Right, so then what did you mean when you said you tested it out of distribution knots?
So, I mean, maybe a better, here's a really caricature example. Imagine that you have someone gives you a list of all elliptic curves that rank 4 and 5 up to some conductor. And then you train a neural network that predicts whether it's ranked 4 or 5. So, but it's incredibly hard to come up with that list. And so you can have this great neural network, but this will be totally useless because you're never going to get an elliptic curve that someone tells you a priori is ranked 4 or 5. That's a really stupid example. And in this particular example, it's very interesting because the wrong conjecture was based on, so there's certain phenomena in knots which only show up when you have 40 or 50 crossings. So it's really, if you imagine this landscape, there's this kind of landscape of stuff you see in crossing number up to 19, and then there's this kind of like these extreme islands that emerge as you go very high crossing number. And it was exactly on these kind of islands that the conjecture is false.
Yeah, I mean, here again, this is a case where ultimately it's a question of counterexamples. So I would agree in that case, once you find a counterexample, this question of distribution is secondary. But for the reasons he was saying, the problem came up for this reason of out of distribution, again, examples were out of distribution.
But see, I understood you to be saying something slightly different, which is that there seems to be some sort of natural partitioning of the space of knot classes in which in each there's some domains in which certain structure arises and other domains of that space, other structure arises. And so you want to have, if you're going to throw a machine learning algorithm at it, you want to have different, you want to learn different function approximators for those parts of the space. Is that right?
It's more, I mean, maybe islands is wrong, like there's incredibly special regions. Like there's many situations in maths where like the generic example will have properties, you know, I don't know, polytopes or something. You sample a random polytope, then you'll have properties. However, there's like very crazy extremal examples at the edge of that you'll never see by random sampling.
Yeah, that's right. That's
But you're saying that the applicability of theorems is uniform across all of those examples.
Well, like as mathematicians,
you're looking for a theorem of that type, yes.
Yeah.
Other terms and then.
So I don't want, this is a very, we have time after 11:30 to get into discussion. Let's save it for some discussion. I think you actually made my point, which is to say that this language of in distribution, out distribution is a good one to keep in mind when doing this stuff. Okay, so reinforcement learning. So this is again going to be a few slides. Okay, so we have there is again a framework in which reinforcement learning can be phrased in terms of states of the system and a set of actions that you state that will take you to a new state. It could be probabilistic, it could be deterministic, but ultimately the rewards, although they are the function that ties them to the state and the action. It's going to be, this is interesting in the case where the rewards aren't immediately tied to the actions now or very recent actions. It could be because of actions taken long before. And so that's a fundamentally different problem that requires some different techniques. And again, a long story, but one of quite a bit of interest to us because many math problems do have that nature. And a good example to get into this, I referred to this 2018 paper, which I believe is the first one that solved the Rubik's Cube using reinforcement learning. And my belief is because around that time, 2017, 2018, this would be like the standard question I would give people at conferences. This reinforcement learning stuff is good and people tried it on the Rubik's Cube. And of course, there was a program solver already in many years before. So from some point of view, it should be possible. But it was a little tricky. And the way these people got it to work was to say, well, let's start with the solve cube and then make configurations where we just do one twist and train it on those, and then two twists, and then three twists, and so forth. And then that is called curriculum learning. The simpler examples first, and that works. And there's some discussion already in the Zula of adapting this to, you can think of those two problems. Of finding short math in the Cayley graph of the Rubik's Cube group. And it's interesting to try and do this for general groups. Okay, another recent success with reinforcement learning is the alpha tensor of the DeepMind that found matrix multiplication algorithms for, it's just long-standing computer science question. What's the minimal number of multiplication operations it takes to multiply two matrices to get a third? That's fewer than the naive algorithm would suggest, and they were able to lower these upper bounds. Okay, large language models, I'm clearly going to use those. And probably the version that's the most relevant for what we'll do in this workshop is code generation. And I'll talk about an example of that shortly. It's really arguably, this is the thing that they do best so far. They are, of course, not reliable, as everybody here has heard. There is also very interesting work trying this out for automating theorem proving, auto-formalization, and other things. Question of terminology. So the transformer models, models with the attention layer that I discussed, talking about mapping sequences of the vectors or sets of vectors into sets of vectors. Then you can use that autoregressive to predict the next item from the previous items. That's an autoregressive model and language model with this language. And then you train it on quote all the text on the internet and you get the large language model. So these are three different concepts and at least in speaking, let's try to keep the distinction. Okay, so now this example I'll talk about is the recent fund search paper, and so they solved a variety of combinatorial optimization problems, such as the cat set problem. So this is, we had talked by Jordan Ellenberg about this last spring, so I'll go quickly. So we're looking at vectors in with elements in the Z3, and we want the largest subset of such vectors so that no triple adds up to 0. Clearly, it's in that combinatorial optimization paradigm that we talked about, and you can try using one of those solvers. But the approach that they did better and improved the bounds. And what was their approach? Their approach was use language models to generate programs that generate a score function that defines these sets. Okay, so just there's an example of the program, but what does the program do? I guess we need to pick out the largest set we can that satisfies the constraints. And their approach is nice because it explicitly exactly implements the constraints. What you do is your program computes a score or priority function on this whole set of vectors, and then you look for the vector that's the highest score. You rank vectors in terms of that score value, and then you just go down the list. And if you're allowed, if adding such a vector violates no constraint, you add it to the set, and you move on. Of course, if it violates, you just throw it away and keep going. So that's called the greedy search. So there's, basically the choices are all determined at that point. And so a function that produces a score on the set of vectors produces a set of vectors which has a size. You're trying to maximize that size. And then what they did was they did basically a genetic search through the space of programs that implement that function, where the language model was doing this essential step of program 1 was pretty good, program 2 was pretty good. I'm going to give those to the language model and say, okay, language model, give me a program like that. And it produces a new program, which is like that. And then you test it out in this way, and if it's good, you add it to the set, you drop a course one, and you do the genetic algorithm. And so that did beat some previous records. This is an example of one of the programs that generated. So it's not asking it to do too much. It's not asking it to do more than run a sensible program that produces a score for each vector. And this program that did beat the record was interpretable enough. It's kind of a weird looking thing, but they were able to define a simple, explicit construction. So very fascinating because it's the large language model, and not only is it this kind of newsworthy thing, it opens the possibility that, well, somehow it used human knowledge, it used some kind of heuristic derived from the huge literature of code and who knows what else, to somehow use those heuristics in producing this program. Well, very optimistic to my mind, but not crazy. It's certainly conceivable that the language model did something smart in producing this program. So that is, to me, a very interesting hypothesis to test. Did it somehow generate this program by a random search, or did it somehow informed by heuristics out there in the literature? Okay, this is a slide about this auto-formalization concept, which was very much emphasized by Kristen Sagan back in 2020, that as we all know now, this was before language models, the obstacle to doing a lot of stuff with formal.
On the last slide, did the machine that generated this program have access just to programs or documentation as well? So you could use like English language reasoning.
I forget because there's more than one of these papers, but that's really an idea out there. This one might have actually. There is a reverse thing where you can take the program and produce documentation and feed that with it, but that might have been a different paper to use. That is a concept which is useful. Yes, I think I'm thinking of a paper of attendant bounds that did that, but maybe this one that I can't remember. Anyways, so we have a relatively small corpus, just lean math lib. The rest of the formal stuff is some millions of lines of formalized mathematics. And of course, we have a much larger corpus of informal human written mathematics. So if we just get the language model to turn informal into formal, and especially if we can go both ways, then we start to get the possibility of this loop where the system can improve itself and start to verify proofs and generate its own proofs and then check them with the verified and so forth. So very powerful possible approach to bootstrapping up the level of the system, which is again starting to become popular. Hopefully we'll get from the leaders of the alpha proof group. They promised to speak to us sometime this semester. Okay, I think I'm going to skip this slide, but this is some questions about using commercial elements. We have some possibility, but we'll announce this later, of getting some credit from the Mistral to do some of these experiments here. Okay, so now we come back to this. What math questions are good for ML and AR, and then I'll go through some more speculative stuff if we have time after this. Okay, well, really it's good if you have a data set relevant to your question. Really, if you have no strong method, it's good to try this. Something where there's been a lot of success, and I'm sure Francois and Tori and I will talk about this, is inverse problems, where there's a simple algorithm to compute the function, and you like to learn the inverse, such as a differentiated function, integrated function. Can you train a network to do integrals that way? There's been success with that. The comment I just made on the previous about the fund search for language models, it's probably a good sign if similar problems are already solved in the corpus. Of course, maybe who knows what similar means in this context, but that suggests that the language model probably has an advantage. I think this is an important one. There are problems where the only known solution is very intricate. Proof of the four-color problem. It's conceivable that that is it. There is no simply proof of the four-color problem. And if you have reasons to think the solution is intricate, then that's a very good reason to bring a computer in from the start. So like this Boolean Pythagorean triples of that many times. So that's a central question here. Can we know to what extent? You generally can't, but to what extent can we have an informed guess of yes, there's some simple solution that we should really be looking for, or no, it's just going to be 10 terabyte proof at the end. What can we do? So that's a central thing. As I mentioned, ultimately machine learning statistical questions are actually, I think, the things to look at, to think more in that vein. To get exact results, and there's a nice paper which is a relatively simple problem that illustrates this point. This was a problem that comes up in string phenomenology. You have a line bundle on a Calabi-Yau manifold on a computer homology, and it's pretty simple. It's like this piecewise linear function of the degrees of the line bundle. But it's a little intricate. It's some work to do all these spectral sequences and stuff. And given some data of that sort, you can learn the answer. It's clear. This is a relative network. You can get these piecewise linear functions. And so that's kind of the approach that says, well, yes, if we had time and energy, we could work out the solution ourselves, but it's not worth it. If the machine can get the exact solution, let's just do it that way. Another, perhaps more, I don't know, deeper or more interesting, the type of work we'll hear about in the week on verifying numerics in PDE, that you can use the machine learning, say, to get an approximate solution to a PDE. And in the past, you would say, oh, that's our evidence. We think such a solution exists. But you can also do a verify calculation against error bounds, and if you can combine that with the neural network, and you can duplicate your solution in a verified way, then that can be the input to a rigorous argument that says that, well, yes, we really have to prove there's an exact solution close to this verified solution. So that's again a good class of questions here, and I'll throw out a couple of cautions. To the extent that you putting very complicated things in. And I don't mean complicated in Jordan's sense that there was a lot of work in making it. I would say the knots of crossings up to 19 might have been hard to get, but it was very simple to describe, very natural sounding thing. But again, my canonical bed noir, the list of graphs in Mathematica. Well, if your result actually depends on that in any essential way, as opposed to, I found a counterexample in that list. That's kind of may not be ideal for math. And then this Feynman's phrase that Cardo called science to say, if I write a paper that looks a lot like a machine learning paper with a math data set, almost a pattern of a machine learning paper. What have I done? That's kind of, if I follow the form, have I accomplished something? So, anyway. Okay, so I have 7 minutes for my questions and speculations. I can put them up here and people can decide if I should continue to discuss them or we should just open it up to a general discussion because we have some time after this. Okay, so this is a big question, which again, the language models are at present not reliable. There's a lot of work on trying to make them. So what can we say about that? Obviously, not a topic that we can really compete on in this workshop. What would it take for a computer to make a discovery in mathematics? AGI clearly would do it. Is there something short of that? So I have papers that claim that computers are making discoveries, but I think we'll have a panel discussion. We'll have a panel discussion on this afternoon, and I think those claims can be criticized. And on the other hand, there is a reasonable set of requirements that could be met in the not too distant future. Okay, well, what if DeMine revolutionized protein folding and other fields? What if they produce a correct root of the Riemann hypothesis in the next few years? And this is it's not the doomsday, certainly the seismic event, it could be in history. And then you can partition this in various ways. And one of the most interesting partitions, of course, is do they release the system code that generated this proof, or do they not? And then we call that the original alpha fold 2 was not originally released until others duplicated it. And they decided to use it as reasons to suspect both things. So, okay, well, I think 2027 is kind of optimistic, but 2037, who knows? What are more conservative possibilities? And then we lead into this question of the Thursday panel. How will advances that seem quite foreseeable as from where we stand now, how will they change the practice of mathematics? So I can continue my remaining 5 minutes, or why not? Since I don't see it. Or is it boost? So okay, so frontiers of language models. I think a lot of the research now has come up.
Can you turn up the volume a little bit?
I will try to turn towards this. My problem is anyways, I will turn towards the microphone and let me again not spend a lot of time on this slide. I basically myself believe that the unreliable reasoning is a big barrier to trying to use this for math and many other things, but there's no fundamental reason why that problem can't be solved, and that probably will be solved in the coming years. Whereas there's other problems that language models as they exist now, the autoregressive ones are bad at problems that involve search, planning, this sort of thing. And this is fundamental basically because it's autoregressive, it makes a step and it's very hard for it to take the step back. But so that's something that requires a change of architecture, possibly including reinforcement learning. That's clearly a topic of research in the industrial labs. And that probably is required to get language models to do any real theorem proving. Okay, I'll say more about this in the panel discussion, but I'll just set out my position and take a little less time about the automated mathematical discovery. And I think, again, there is this interesting literature, which is actually a very nice review, which few people seem to know about, like Colton, Bundy, and Walsh, of the earlier old-fashioned AI approaches to math discovery. There were systems that were pretty interesting, that their conjectures led to tens of math papers proving, not the deepest conjectures, but at least something non-trivial. But you could really debate whether either of those most successful things should be counted as having automatically discovered something. And I would say, basically the reductive absurdum is that every time you compute something with the computer, did it discover the answer? Well, no, it didn't discover the answer. So not every computation is a discovery. So what makes it count as a discovery? There's some question of definition there. But I will argue in the panel that it should have, well, again, the other reductive absurdity, which I'll get to, is there is an algorithm to generate all provable mathematical statements, and you just iterate this is the search tree. Of course, it's exponentially slow. It's useless, but in that sense, do you count that thing as having discovered those mathematical statements? Well, no, because it didn't make any choices. It has to choose to look at certain computations, a tiny subset of the possibilities, and then there has to be something saying, yes, this was a significant discovery. And
Does
the
it have to be the same agent?
no, I'm only saying agent is a big broad and multi whatever thing. No. But it should be without humans. And so
You're saying without a human.
without a human, that's what automated means. That's what I mean. No, but
There's no human saying this is a significant.
exactly, there's some, well, in the existing systems, what it is there's some function that says that, yes, this guy I consider interesting, let's keep it on the list, like the fun search. The fun search had exactly that. It had a ranking of, we posed a problem. The problem was find the biggest cat set. And so that was a ranking function. So now these systems have heuristic ranking functions to say, this is interesting, this is more interesting than it was a separate ordered list.
Well, the part that I don't understand about this is that presumably at the end of the day, there's a human mathematician who says this is an interesting discovery, right?
Well, that's like the validation, I would say. There's the systems processing, and then there's the human. That's right. I mean, we can reduce the need for the human in the loop.
Yeah.
And then there's this question, how far would it get if you took the human out of the loop? And all existing systems figure out very quickly. It's clear that whatever you're using to judge intrusiveness doesn't go very far, doesn't generalize. So that's the real test. So anyway, it's something that we'll discuss this afternoon. And I believe it is possible. I believe it's possible to get an interesting definition, which computers will do. I believe from reading the news as you all do that if we get these quantum advances in AI, if we get scientific agreement, there's going to be a huge pressure not to make it public. And this will lead to a further crisis in our field. And you can read again. There was this exchange of letters between public letters between Mark Zuckerberg and Sam Altman, which outlines many of the issues on both sides of the open source language model today, and both the incredible value of the system, which the proving system is very much in computer science. It's more or less the same field of formal methods as verifying software, which is an ability which is easily worth trillions of dollars a year. So is DeepMind going to publish that? Well, from the argument, the answer is no. And then suppose they want to publish it, and then people in the government bureau in the UK say, yeah, but now you're giving it to the Chinese, don't publish it. So these are real things to think about. Okay, so these are these more modest milestones, which I do expect to see in this decade. And talking about these kind of things in 2030 talk. Definitely a system which makes proofs much easier to construct and then verify. And now these others are kind of interesting in the sense that they're so poorly defined. They're the kind of standard tests of the effectiveness of machine learning. Can we make a system that increases productivity by a factor of 10? Well, this is what's happening for software writing. Again, language models generating code is those programs are getting massive boosts of their productivity. Even the limited measurements people are 50%. And factor of 10 maybe. But how do you quantify that? Software, people can count lines of code and have some meaning, but we do not count. Well, we do count numbers of papers, but everybody mercilessly criticizes that measure. So, nevertheless, isn't this a valuable goal? How do we measure it?
Is the boost in programmer productivity constant across skill level of the program?
Probably not. No, this is very little study so far.
Or what do you think? Is the best programmers are helped less? Or?
Well, there's no reason for it to be constant, but I would guess they all get help significantly. Yes, at every level, the best programmers can produce massive things and quickly judge if they're correct or not. The worst programmers don't have to go to their manuals so often. Yep. Okay, and then we get to this even, in some ways, equally desirable outcome, system that speeds up learning essentially by a factor of 10. How do you quantify that? Isn't it right to try to quantify it? If we're going through this machine learning paradigm, so much success just comes from having objective functions and quantifying these things well. Wouldn't we being on, but I carefully applying the same philosophy to our human activities. Okay, and then my obligatory AGI beyond the slide. And again, there's arguments both ways, but clearly fundamental obstacles to this point to having AGI and many people would say 20-year time scale, or FX early estimate based on the computing power was 2030. And that factor would clearly have met. There's clearly other things needed, but again, no fundamental barrier. So it's exciting times, and we will join it in our position as mathematicians and machine learning researchers working together. So thanks to everybody for listening and for